All right. Hello, everyone, and thanks for attending today's CGD seminar. Before we get started, I'll remind everyone our Cgd Code of Conduct at these seminars, where we share the air, acknowledge teamwork, encourage innovation, show appreciation, consider new ideas, and offer constructive feedback. I'll also ask that everyone please keep themselves muted and hold any questions until the end. If you have any clarifying questions, then you can put them in the chat, and I can ask them during the talk as necessary. Now it's my pleasure to introduce today's speaker. Hansi Singh is assistant professor in the School of Earth and Ocean Sciences at the University of Victoria. She received a bachelor's in physics from Rice University and a master's in applied math and PhD in atmospheric sciences from the University of Washington. Afterwards, she held the Linus Pauling Distinguished Postdoctoral Fellowship at the Pacific Northwest National Laboratory. Her research interests include coupled climate dynamics and feedbacks, Earth system modeling, and polar climate change. Her talk title today is Anticipating Climate Change over Antarctica, Means and Extremes over a Warming Ice Sheet. So Hansi, feel free to share your screen and take it away.
Great. Thank you so much for that kind introduction, Dan. I appreciate it. So thank you so much for having me. We're still extreme, or we're still, we're still far away from each other, not in person, we're remote. And of course, it would be great at some point for us to, be in person, but here we are again, yet another remote seminar to attend. So thank you for having me. So this is work today that I'll be presenting with several co-authors, as well as members of my research group. So co-authors, Lorenzo Polvani, Phil Rash, Adriana Bailey, and Jesse Nussbaumer, a couple of those folks right here at NCAR. And then with members of my research group, postdoc Ariel Morrison, graduate student Kyle Hayblom, and undergraduate honors student Brendan Dyke. So to begin, I'd like to offer some motivation about the Antarctic. So why might we want to study such a cold and remote continent? So this is literally the cutest reason, especially if you're into crustaceans. This is the Southern Ocean krill. It forms the base of the global ocean food chain. And as waters around the Antarctic continent warm, its breeding habits are changing. There are less krill, not to mention just people love to catch these things because they have nice oils on them. So regardless, these creatures are, their populations are declining, and this affects fisheries around the world. So really what happens in our Antarctic doesn't necessarily stay in the Antarctic. The other thing I'd like to point out is that what happens over the Antarctic is going to determine what sea level rise we see by the end of century or even mid-century. So this is from the IPCC AR5. I know we have a new one from AR6. Regardless, when we look at future projections of Antarctic change, what we see is a large spread, and a lot of this spread is going to depend on us and our emissions, of course, but a lot of this is going to depend on how the Antarctic responds. So we really care about what happens in this cold and remote place. And finally, when it comes to understanding past climates, we have a very good sense of what these past climates might have looked like through these amazing time machines, these ice cores. And so, we really want to understand what Antarctic climate looks like today, in the past, and into the future. And understanding the past may hold the key for understanding the future. So, this is like a very obvious thing, but, the Antarctic is just not like the Arctic in so many ways. So when we think polar, we think Arctic, we think all of the exciting things about the Antarctic, and yet, or the Arctic, and yet the Antarctic is quite different, even though it also is a polar region on our planet. First of all, unlike the Arctic, it has a seasonal ice pack. That means that the sea ice around the continent grows and melts yearly. So this actually constitutes an area that is about equal to the area of the continent itself. And if you're not convinced that the continent is big, this is the continental US superimposed on Antarctica. And you can just see, this is from NASA. It's a big place. It's a big cold place. the second thing is, of course, we have this amazing Southern Ocean, which is circumpolar. And so, we have this ACC current that flows through it. It is also the only place where we actually have upwelling from intermediate and deep waters directly to the surface. And this is made possible by, the enormous winds that are going over that ocean. And finally, this is what I'm going to focus on today, namely the surface climate over this amazing continent itself, which is just on the top of the continent is an enormous ice sheet. So at its thickest, this ice sheet is nearly 4 kilometers. And you can see that while the whole continent is quite a substantial ice sheet, the West Antarctic, shown here, has a very different characteristic compared to the East Antarctic. So the East Antarctic is very cold and dry. The West Antarctic is warmer and moister. And it is also grounded. The ice is grounded below sea level. So that makes it particularly vulnerable to rapid retreat in the future, provided that, we continue on our warming trajectory. So the Antarctic response to climate change has been mixed, of course. So ocean temperatures have increased. This is from Boning et al. 2018, subsurface ocean temperatures certainly. On the other hand, the sea ice, at least for, about 35 years here, it was merely increasing in area. This was until 2015. Following 2015, there was kind of an abrupt drop off. Then there was a recovery. And then this year, the ice is still lower than usual. So, who knows what the Antarctic ice is going to do next. So it's been a fun show to watch, but certainly we're not seeing the kind of decline that we see in the Arctic, steady decline in the Antarctic. And then finally, surface warming has been really muted. So this is the NOAA MLOS data set. This figure that I have here only goes to 2014. I think that if you looked at it in later years, so up to 2022, I think you would see a little bit of warming, perhaps particularly over the West Antarctic. But in general, like the East Antarctic has just remained cold and dry, even though, just recently we had that spectacular heat wave event. So, and this is in comparison to the Arctic, which has really seen substantial amounts of warming that is certainly polar amplified, at least 2 to 3 times that of the global mean warming. So in this talk, my focus is really going to be on what sets the Antarctic apart. And this is, I believe, the high orography of the Antarctic continent. I'm going to show that the high orography of the Antarctic continent impacts its sensitivity to warming, as well as the efficacy of poleward moisture transport. I will also show that over the Antarctic continent, extreme heat events are going to become more intense by the end of the century, and low-lying regions in particular will experience more surface melt, okay? And so once again, we get to this idea of how important orography is. Really, the high elevation regions like the plateau will experience sort of fewer surface impacts than these low-lying regions. And these low-lying regions, as I said already, including the West Antarctic ice sheet, are already uniquely vulnerable because of the fact that that ice sheet is rooted below sea level. So to begin, I want to motivate by thinking about the radiative feedbacks over the Arctic versus the Antarctic. So here's that, figure contrasting current warming over the Arctic versus the Antarctic, showing how the Antarctic seems particularly resistant to warming. And so if we look at the radiative feedback, so these are a bunch of experiments using CSM1 with a slab ocean. The Arctic feedbacks are shown on the x-axis, the Antarctic feedbacks are shown on the y-axis. And the one-to-one line is this line here. And what we see is that in general, the Arctic feedbacks are all more positive than the Antarctic feedbacks, though there are a few feedbacks that really jump out at us. The one that jumps out the most, I think, is the lapse rate feedback. So the circle is a CO2 doubling experiment only, and then the little dots have different amounts of ocean heat uptake that we added in there. Whatever you seem to do to this to this continent, it seems that the Arctic is just more sensitive than the Antarctic. And it seems like the lapse rate feedback is the one that is perhaps most implicated here. So if we look at the lapse rate feedback over the Arctic in winter and the Antarctic over its winter, what we notice is that lapse rate feedback is very positive over regions with sea ice loss. Sea ice loss regions are shown in the green contours. And so we see a really strong positive lapse rate feedback because surface amplified warming is really enhanced where we have sea ice loss. However, you notice that boreal land regions in the Arctic also show a lot of low-level warming, and we simply don't see that over the Antarctic. So the Antarctic continent seems, surprisingly resistant to having a positive lapse rate feedback. And the one area in the Arctic that you might notice looks similar is Greenland, right? These are both high and dry ice sheets. So maybe the reason for the reduced sensitivity over the Antarctic continent is perhaps its peculiar orography, the fact that we have a giant ice mountain sitting over the pole. So this is easy to test, actually, and fun to test if we have models. And so what we did was we ran a series of experiments where we doubled CO2 in a base climate state where Antarctica is tall. When I say tall, I just mean its present day size. And then we ran another set of experiments where we doubled CO2 when Antarctica was flat in its base state. And here we use two fully coupled GCMs in order to really get a good sense of whether the results that we got were robust. We used the CCSM4 and the CSM1. So we ran these before CSM2 was in common use. So that's why these are CSM1, not CSM2. And the fundamental result that we got is that with CO2 doubling, there is certainly greater warming over Antarctica when it's flat compared to when it's tall. So on the left here, I show the warming on the top in CSM, on the bottom in CCSM4, when Antarctica is its present day elevation. And then the warming with CO2 doubling when Antarctica is flat in CSM1 and in CCSM4. So in both cases, we see that there's a lot more warming, particularly over the super vulnerable area, the West Antarctic, when Antarctica is flat compared to when it's tall and we subject it to CO2 doubling. Now, we might wonder why this is the case, and I'm going to argue that this is really because of dynamics, namely the dynamics of energy transport towards the continent. So moisture transport in general increases more towards the Antarctic continent with CO2 doubling when it is flat compared to when it is tall. So here, tall Antarctica is the change in the latent heat transport is shown in blue. And then the dashed line shows the change in the latent heat transport when Antarctica is flat with CO2 doubling. And what we see is that there is just more poleward latent heat transport when Antarctica is flat compared to when it is tall. So we might wonder why this is the case. Why would there be more latent heat transport towards the Antarctic continent when it is tall compared to when it is flat? So to understand these, we can look at moist isentropic surfaces. So here what I show is on the top, the moist isentropic surfaces. These are the contours of constant moist static energy. This is shown as the zonal mean, pressure in the vertical coordinate here, and latitude in the horizontal coordinate. So the lines are the contours of constant moist entropy. And what we see is that when Antarctica is flat, these lines are much flatter compared to when it is tall. Okay, and so what we note is that if we look at the change in the specific humidity. So the specific humidity response to CO2 doubling. What we see is that specific humidity decreases a lot less along these flat, moist isentropic contours than along these tall, moist isentropic contours. And this makes a lot of sense because if your geopotential is increasing along a moist isentropic contour, then your latent heat is probably decreasing, right? It's like a seesaw. And so geopotential increases less along a moist isentrope when Antarctica is flat. So therefore, more moisture makes it to the pole. Air parcels retain more moisture as they move poleward towards the continent. And the gradient of the change in the specific humidity along a moist isentropic contour is less when Antarctica is flat than when it is tall. So more moisture just makes it to the continent. The other reason, this is also a dynamics reason, is because of dry processes. So this is kind of like a fun thing that we note when Antarctica is tall versus when it is flat. So what I show in the contours here are the control meridional stream function, the overturning stream function in the atmosphere, pressure in the vertical, latitude in the horizontal. And so these stream functions show the polar cell, and we can see the polar cell really well in the tall Antarctic case right here in both models. Left is CCSM, right is CCSM4. And then if we look in the flat Antarctic case, there's literally not a polar cell, like it's just gone. So, the presence of that strong polar cell really depends on the orography of that continent. Now, what we note is that when we have a polar cell, I show the temperature advection response to CO2 doubling in colors. When we have a polar cell, we actually have temperature advection away from the continent. So this is shown in the purple here. We see it more weakly in the CCSM4 as well. On the other hand, when we have a flattened Antarctica and we double CO2, we note that there is this lovely low level advection, warm temperature advection towards the continent. I would argue that this is very similar to potentially what happens when you remove or when you have sea ice loss over the Arctic. You have sea ice loss over the Arctic, and so then you have warmer temperatures over ocean that doesn't have sea ice, and then this gets advected to boreal land regions. This is very similar to probably what is going on here. When you don't have that same orography, that high orography, you just have much more efficient temperature advection towards the pole, and therefore it warms more. So what we see is that when we have a flat Antarctica versus a tall Antarctica, warming in the lower troposphere is much more surface amplified. This is true in both the CSM and the CCSM4. And so we have a much stronger lapse rate feedback. So here is the lapse rate feedback in the case where Antarctica is tall, and here it is when Antarctica is flat. And once again, we see that it is a larger lapse rate feedback because we have more surface amplified warming. And the most interesting detail, I think, is just how the West Antarctic really jumps out here in terms of the region where we expect to have the strongest response if Antarctica were to be flattened. So clearly, Antarctic orography is really important for dynamics and in particular transport towards the Antarctic continent, poleward transport, and in particular poleward transport of moisture. So from that point, I'm going to move to thinking more carefully about the hydrologic cycle over the Antarctic continent. And the way that I like to think about the hydrologic cycle is I like to think about it from a source to receptor perspective. And this is a perspective that is made possible using numerical water tracers. So here I'm kind of showing some of the cool things that you can do with numerical water tracers. So here I show the source of Antarctic precipitation by latitude with the contours of the surface elevation also shown. And what you see is that high surface elevation regions have moisture that comes from more equatorward sources than low-lying regions. Low-lying regions have moisture that come from more poleward sources. So higher elevation sites receive moisture from more equatorward sources than low elevation sites. In other words, orography really matters for the hydrologic cycle and moisture transport in particular for the Antarctic continent. And of course, this makes a big difference in terms of thinking about surface mass balance for this giant thing. So what are numerical water tracers? I know many folks are familiar with these, but in case some folks are not familiar. So with numerical water tracers, these are available in CSM1, and I believe they are now possibly being worked on in CSM2, or maybe they're already available. There's some cool work that I think Tree Dutta is doing, as well as, and maybe Jesse Nussbaumer is involved, and Jan Lennart. So anyhow, there's a lot of cool work going on in terms of understanding surface mass balance over the polar regions using numerical water tracers. So what are these? What they allow us to do is tag moisture at its point of evaporation, follow it through advection and phase changes, and basically the tag remains up to the point of precipitation. So in other words, this allows us to establish a source through transport to receptor perspective on the hydrologic cycle. We know where moisture came from and where it arrives. So based on the fact that extrapolar moisture transport closely forms moist isentropic surfaces. This is something that, I pointed out earlier when we were looking at those flattened Antarctic experiments. We can consider the moist isentropic surfaces as almost being like a stream function of poleward moisture transport. What we note is that more distant moisture sources bring moisture over the Antarctic continent. This is what I show here, the vertical profile of moisture over the Antarctic continent, in particular, the fraction that comes from different regions. More distant regions bring moisture much higher in the atmospheric column, and more proximal regions bring moisture much lower. So, for example, if we're on the Antarctic plateau, which is, perhaps around, 500 or 600 millibars in surface pressure, most of the moisture there is going to come from between 40 and 50 south, for example. Whereas if we're at much lower lying regions, it is more easy for moisture to come from more proximal sources, perhaps even regions that are within the area of the ice pack. And so if we look at this in the latitude height plane, so here I am just looking at moisture that comes from 30 south to 40 south. What we can see is that really this moisture does kind of lazily follow these moist isentropic surfaces. So this shows the fraction of moisture. Red means that there's more of a fraction that is coming from this particular location, 30 to 40 south. And the contours are once again the contours of constant moist entropy. So this makes it sort of look like, the moisture transport to the Antarctic continent is like a fire hose. In fact, it is not like a fire hose. So here's a figure, just jumping to CSM2 because there was some super cool data that is available online thanks to AWS and the CSM2 large ensemble folks. This is 3-hourly data over the Antarctic continent, and this is in particular the integrated vapor transport anomaly. Thanks to my undergraduate student, Brendan Dyke, for making this animation. He's actually looking at these moist air intrusions / polar atmospheric rivers over the Antarctic continent within the CSM2 large ensemble right now. And so One thing that you can notice here, the red regions are regions where we have a lot of moisture transport towards the continent, and you can really see that, it's kind of hard to get moisture perhaps to the plateau, though it does happen, whereas these incursions of moisture to the West Antarctic are much more common. And you just see that with sort of more of these, filamentous structures coming into this region. So in general, the West Antarctic is wetter, it experiences more frequent moisture intrusions, and the East Antarctic is drier and experiences less frequent moisture intrusions. We can also try to understand this using numerical water tracers. So if we look at the moisture sources for the full Antarctic continent, so this is the column integrated vapor in the top row, and in the bottom row, I show the moisture source, and this is the percentage coming from each 10 by 10 degree grid cell. So we came up with this cool method where you can actually just put in, I think we put in 56 tags, and yet we can get, use a convolution calculation to calculate the amount of moisture coming from 10 by 10 degree grid cells. So that was kind of exciting. And that's why you see these very sort of more detailed maps than I think we're usually used to when we look at moisture sources. So for the full Antarctic continent, so you can see that this is where moisture comes from in winter. However, for the West Antarctic, it is much wetter, and moisture comes in from particularly the Central and the West Pacific. And for the East Antarctic, here, which is higher and drier, moisture is coming in from the South Atlantic and the Indian basins. So moisture sources to different parts of the continent are quite different. And of course, it's interesting to note that the West Antarctic is the wetter area. And of course, it is also the area that plays very significantly with the Pacific. So I don't think that these things are, by coincidence. It's really like this area is much more vulnerable to incursions of moisture because of the surrounding dynamics of that region. One thing you'll also notice is that West Antarctic moisture generally comes from closer to the continent, closer to 50 or 55 south, whereas for the East Antarctic, moisture comes from much further away, generally closer to 45 south or even more equatorward than that. So here is a super fun animation where we can look at how, and this is a day-to-day animation, CSM1 equipped with these cool water tracers. And we are looking on the left at the temperature anomaly over the Antarctic continent. At the center is the column integrated vapor. On the right is the source of the vapor over the continent. So there's a lot of cool things to look at here, and it's sort of fun to just stare at this for a long time. So essentially, as soon as moisture intrusions happen, they are generally associated with warmer than average temperatures. However, what you'll notice is that the amount of moisture that comes into the West Antarctic is much larger than the amount that comes into the East Antarctic. So over the West Antarctic, we see these large, really significant intrusions. Huge areas of the South Pacific get highlighted. On the other hand, with the East Antarctic, we can actually, cause significant changes in the temperature, excursions in the temperature, warming due to more moisture coming in with not quite as much moisture. And so in general, we note that moisture intrusions lead to anomalously warm temperatures, and that they are associated with subtropical and mid-latitude moisture sources, as shown here. And here, this is shown as millimeters of moisture that are coming from each 10-degree defined grid cell. And that intrusions are much more common over the West Antarctic. Those smaller intrusions are pretty effective at instigating temperature anomalies and warming over the East Antarctic. So warming, moisture transport, and evaporation from these, mid-latitude and subtropical sources all go hand in hand when it comes to the Antarctic. Yeah, I can literally watch this all day. So I'm just gonna let it go to 150 and then I'll stop. Okay, fun. So now, how does moisture transport change as the climate warms? So to understand this, we can start with the fundamental equation of hydrology. And so we can then use the thermodynamics and dynamics framework introduced by Held and Soden for the hydrologic response to greenhouse gas warming. And so the fundamental equation of hydrology says that the difference between precipitation and evaporation must be balanced by the convergence of the moisture flux, BQ. And so in a warmer world, if we assume that the moisture flux scales with the temperature, with the scaling factor being the Clausius-Clapeyron rate, we can say that the perturbed, or in other words, the change in the precipitation minus evaporation, the perturbation response, is simply a scaling of the original precipitation minus evaporation times the change in temperature and the Clausius-Clapeyron scaling. So this is, an argument that's super, super well known in the literature, and there's been a lot of work on thinking about this mechanism. So what this means, of course, is that, you might say that the hydrologic cycle sensitivity to warming is well approximated just by thermodynamics, namely that the wet get wetter and the dry get drier. And of course, the corollary to this is that poleward moisture transport increases as you warm the planet. However, because, this thermodynamic component is so large and robust, perhaps dynamics doesn't matter that much. Maybe it's small, maybe it's not robust. Models disagree, can kind of throw our hands up. But I would argue that this is actually not the full story. Oops. Okay. So sorry, there's a little block that didn't come up there. Okay, so I would argue that this is not the full story. And so the reason for that is when we consider moisture transport from a source to receptor perspective, we can define something called the moisture depletion rate. This is gamma. This is the precipitation divided by the column integrated vapor Q. And the inverse of gamma is the moisture residence time. And so the change in the moisture depletion rate can be written as follows here. And if we look at the contributions from the change in precipitation versus the change in the moisture, the column integrated moisture, precipitation only increases by 2 to 3% per degree Kelvin due to limitations in the rate of radiative cooling of the atmosphere. However, atmospheric moisture increases by 7%, approximately the Clausius-Clapeyron rate. What this means is that the moisture depletion tendency tends to decline as the planet warms, and the moisture residence time increases. And in fact, if we use water tracers and we do this calculation, you can see that the increase in the moisture residence time is really robust. In general, it's about a day. Moisture lives in the atmosphere for about a day longer when you double CO2 because of this increase in the moisture residence time and this decrease of the moisture depletion. So what does this mean for moisture transport? Well, we can define a moisture transport length scale lambda as the advective velocity of the moisture divided by the moisture depletion rate. And so if we assume that V is generally invariant or only changes slightly, we can see that the moisture transport length scale must increase as you warm the planet. And in fact, if we use numerical water tracers, we see that this is, in fact, how atmospheric moisture transport from a source to receptor perspective responds when you warm the planet. The distance between moisture sources and sinks increases. The local contribution to precipitation declines, in other words, moisture that is sourced from local sources, and remote contributions to precipitation increase. So in general, everything is aligned with the fact that the distance that moisture transports is being transported increases. So moisture moving poleward, therefore, perhaps it comes from more equatorward sources. And in fact, we can make some moist isentropic arguments that also suggest that moisture moving poleward must come from more distant sources. Like you can actually write a cute little proof if you wanted to. If you assume that the moist isentropic surfaces simply shift and they don't change shape, then, and you use the fact that atmospheric moisture scales with the Clausius-Clapeyron relation, you generally get that polar moisture must come from more distant sources in a warmer world. Now, is this actually what we see from numerical water tracers? Well, it turns out that we don't. And this is actually because there's some interesting things going on with compensatory behavior due to seasonality over the polar regions. And as we know, the polar regions are highly seasonal. It turns out that in summer, we do see that generally moisture over the Antarctic continent and surrounding oceans comes from more equatorward sources. However, in winter, we find that it comes from more proximal sources. And so in the annual mean, generally, it looks like it's weakly coming from more proximal sources. Why is this the case? Well, it is because of the strong seasonality associated with sea ice loss. So this is sea ice changes in summer, and then sea ice changes in winter. And in winter in particular, the colors show the change in the surface evaporation, contours show the change in the sea ice fraction. And what we see is that there are regions where there is a lot of enhanced surface evaporation surrounding the Antarctic continent. And so what this means is that there's a huge new source of moisture for the continent. And so this sort of overwhelms arguments that we might make regarding how moisture transport should be coming from more distant sources. And in fact, we see this over the Arctic as well as the Antarctic. In general, when you warm the planet, moisture tends to come from more proximal sources over these regions because of enhanced surface evaporation over areas where sea ice has retreated. So seasonality really matters. The polar climate response, in particular the presence or absence of sea ice, really matters. So there's many remaining questions here. My biggest question is like, I've made so many arguments about how hard it is to get moisture to the top of this high and dry continent. And yet now we see that, these proximal regions where sea ice is lost seem to be doing a good job getting moisture to the Antarctic continent. So why is that the case? So we actually think this is some, work that Adriana Bailey and I have been sort of discussing. We think that there's actually possibly changes in the moist isentropes themselves. It actually turns out that the moist isentropes, they seem to rise when you double CO2. And so this would suggest that maybe it is easier to get moisture from more proximal sources to, the Antarctic plateau or other high elevation sites of the continent. And then there's also questions about whether there are changes in the time variance of the moist isentrope. So these are areas that we're still kind of interested in, and I think there's a lot to do in terms of understanding how moisture transport to the Antarctic continent changes as the climate warms. So I'm going to just check the time, make sure I still have time. Okay, perfect. Okay, so the final part of my talk that I'd like to touch on is to think about future projections of Antarctic warming, particularly over the ice sheet itself. So this is work giving a big shout out to my postdoc, Ariel Morrison, and my graduate student, Kyle Hayblom, for all of their really hard work in putting together this study on future projections of extreme events in summer over the Antarctic continent. So, if you warm the planet, eventually the Antarctic will warm. And so what we did is we looked at not only warming over the Antarctic continent in summer, but extreme events over the Antarctic continent. We looked at 29 Earth system models from CMIP6, subject to the SSP 585 scenario. And all of the following look at, the last 30 years of the 21st century compared to a baseline period, 1950 to 1980. And this shows the surface warming over the Antarctic continent in these models. So all of these models show mean surface warming in summer over the Antarctic continent. Now, what about extremes? Well, the fundamental result that I think is interesting is that certain areas of the continent are going to experience more melt days when you warm the planet. So over regions of the West Antarctic ice sheet and the Antarctic Peninsula, we expect that the number of summer season melt days actually like quadruples. So some regions, you have about 2.5 days today. In the future, you might have up to 10 days where these regions are melting at the surface. So, this is not really a surprise, I think. Now, what about if we use definitions of heat waves to look at extremes? So just to, think about how a heat wave is defined. So heat wave calculations, they're generally done for the mid-latitudes and the tropics. And many papers define them as follows. It's daily Tmax exceeding the 90th percentile for at least 3 consecutive days. So you can't just have one day where you exceed the 90th. You have to exceed it for 3 consecutive days, at least. And you use the actual shape of the temperature distribution from a baseline period to define that 90th percentile, okay? And then future periods are generally detrended for the persistence and the frequency calculations in order to calculate the changes in heat wave persistence and frequency. So in other words, we use the temperature distribution from the baseline and everything else is compared to the baseline once we have detrended it to match the baseline. And so if we look at heat waves in particular the intensity, what we see is that generally the intensity of heat waves does increase, and it increases most over the Antarctic plateau, the region defined by the dashed contour compared to the rest of the continent. However, the interesting thing is that if we start looking at the persistence and the frequency of heat waves, we actually see a puzzling decline. So, initially when we looked at this, we were like, gosh, that's really strange that you might see a decline. Is this dynamics? Is there some, decline in, the frequency of moist intrusions? Is there some cool, fun transport-based mechanism for this? So why do frequency and persistence decrease in CMIP6 models at the end of the century? Well, it turns out that the explanation is much more mundane than dynamics. So it turns out that day-to-day temperature variability over the Antarctic continent declines when you warm the planet. And this is the change in the day-to-day variability in summer. And so this suggests that there is a narrowing of the temperature distribution. So we can actually look at that temperature distribution by looking at a representative area over the Antarctic plateau first. So over this area of the Antarctic plateau, so let me walk through this figure because there's a lot going on here. So the baseline period distribution is shown in gray. You can see that kind of sitting under the end of 21st century distribution shown in green. And what we've done, of course, which remember I said that the two distributions are matched up when we calculate the frequency of heat waves and the persistence of heat waves. So what this means is that we put the distributions on top of each other such that their means match. And then the 90th percentile, which is what we compute using the baseline period distribution, now is used to calculate the frequency and persistence of heat waves over future time periods. And so one thing that's interesting to note is that for the baseline period, note where 0 degrees falls. This is a special number, right? Because it is the number that defines when the ice sheet starts melting. And of course, until the ice sheet is gone, until all the surface ice is gone, it is difficult for surface air temperatures to exceed this number. And then we see for the future distribution where 0 degrees falls. So that is what this second horizontal axis is for, shown above. And now, once again, we see that the edge of the distribution, once again, is hitting 0 degrees. And in fact, because it's pretty tough to exceed the 0 degrees, we see that the distribution at the upper end certainly narrows. And so therefore, we have fewer days that wherein this 90th percentile cutoff is actually a thing. And in fact, we see this even more strongly when we look at a representative area over the West Antarctic and coastal regions. So in this case, once again, green is the end of century distribution. The gray is the baseline period distribution. The means, we make them match. And this cool peak here is the 0 degree peak. This is because the near surface air temperatures are often hitting 0 degrees and are even exceeding 0 degrees a little bit. However, 0 degrees is certainly a soft constraint on how high surface air temperatures can go. And so because of this, the PDF at this side must narrow. And so because we're defining the 90th percentile for heat waves based on the baseline period, it means that we have less area, shown in green here, fewer number of days where the distribution actually exceeds this 90th percentile, because that would mean that the temperature has to actually be above freezing. And it's hard to get surface air temperatures above freezing when you're dealing with an ice sheet. So I think this constitutes a bit of a cautionary tale when we try to take extrapolar metrics and apply them to ice-covered regions such as, Greenland or Antarctica. Because surface air temperatures over the Antarctic continent are constrained by the melting point, I would argue that perhaps conventional heat wave metrics, the ones that we use in the mid-latitudes and the tropics, are probably not the best suited. Probably simply looking at melt days are the best metric to use. So that is perhaps a lesson learned for us as we put together this study. And so you can actually find this on Earth Archive, or yes, SOARS actually, we've already posted it and it is currently in review. So thank you so much for having me. I'll put up my summarizing points, namely that the high orography of the Antarctic continent impacts its sensitivity to warming, including how much poleward moisture transport can increase when we increase atmospheric CO2. Second, that the regional orography of the Antarctic continent impacts moisture transport, and of course that the seasonality of sea ice in particular complicates how moisture transport changes as we warm the continent. And then finally, in the future, I've shown that once again, orography is important. Lower elevation regions of Antarctica will almost certainly experience more and frequent melt days as the planet warms. And so thank you so much. And I'm happy to hang out and answer any and all questions.
Excellent. Thank you so much, Hansi. We have time for some questions. So folks can please feel free to raise a hand or enter a question in the chat, and I'm happy to read it out loud as well. Okay, a couple of questions. Hyan, go ahead.
Nice talk, Hansi. I wonder whether you could comment on the dynamical change, such as whether how the topography can alter the stationary waves, and also how does the topography can impact the storm intensity. Mainly, I'm asking about change in V bar and the V prime.
Yeah, thank you so much for that question. So we actually looked at this in my 2016 paper. So in the 2016 paper, we looked at the climate response to flattening Antarctica. Um, these are experiments that have just kind of been run, many times, in the past using models of increasing complexity as our Earth system models have gotten more complex. So, for example, Carlos Machoso was the first one to run these super cool experiments, where he flattened Antarctica and looked at the atmospheric response. And so, yes, in terms of understanding how the waves change and the dynamics changes. Certainly, it has been reported that the polar cell declines, and this is probably due to declining wave activity that was instigated by orography. And when there's no orography, you don't get the same wave activity. And then there's also some interesting details about the weakening of the eddy-driven jet when you flatten the continent. However, there's also the fact that even though baroclinicity decreases further away from the continent, it actually, like over the Southern Ocean, when you flatten Antarctica, baroclinicity actually increases over the continent itself. So there's kind of this like sort of tug of war happening between sort of these different factors. In general, there's less baroclinicity everywhere, but there's more baroclinicity over the continent. And so these are all sort of details of changes in the dynamics that we discussed in our previous paper from 2016. And so I do think that all of those come into play when we look at the CO2 doubling response.
Thank you.
Thank you. I think Clara was next. Clara, if you're trying to speak, we can't hear you. Maybe we can move to Marika for the moment.
Hi, surprise, it's actually Alice and Marika. We're having a watch party. So first, well done. My question was about the extremes on kind of on top of the Eastern Antarctic ice shelf. So you were saying that those didn't change a whole lot in the future, but these are simulations where we don't actually have a change, like the ice sheet isn't active, right? So we don't actually know how the elevation would change with time. So I was just kind of wondering if you had any speculation or comments about how you think that might affect your results, and if there are any things from maybe the ISMIP or whatever it's called, looking at how surface elevation over East Antarctica might change in the future that would affect this.
Yeah, so that's an awesome question. And there are some folks that our group is collaborating with who are potentially going to be doing some of these experiments. To 2100, it's a good question. I mean, certainly, like, I think that it's possible to see changes in surface elevation over the West Antarctic, and maybe some of those would be significant enough to year 2100 to, change the dynamics, increase moisture transport, activate this kind of dynamic feedback that would enhance surface melt. On the other hand, though, I think, to year 2100, perhaps this is not necessarily a huge and important factor over the East Antarctic. On the other hand, some of these experiments that we're planning to run them up to changes in topography to year 2300, in which case maybe then we would see changes in the East Antarctic. However, over the East Antarctic, there's so much more snow, maybe it would actually rise. Like maybe you would see kind of like this negative feedback, right? And so then maybe moisture transport to the East Antarctic would actually, I don't know, it would actually, like, there's more precipitation. Maybe the surface mass balance would be such that that area changed little, or maybe actually increase. So who knows what we would see, but we are excited to run these experiments and see what changes in, more realistic changes in topography might have on some of these results. Because right now there's no active ice sheets in any of this.
Excellent, thank you. Clara has followed up with a question in the chat. She says, as a follow-up to Hyan's question, is the mean present-day polar cell weaker in the Arctic than Antarctic due to differences in orography?
Yeah, I think that is right. I think it is primarily the fact that you have this giant, orographic feature over the South Pole that results in such a strong polar cell, and also results in a really strong eddy-driven jet in the Southern Hemisphere, because we see those practically collapse when you flatten the continent. And once again, this is from that 2016 paper. I don't think that we went as far as to claim that this is, like we didn't compare the Arctic and the Antarctic in that case, because we were looking at coupled responses, and there were some really interesting coupled responses that arise. Like when you change the Antarctic, it actually changes the ocean overturning circulation, which actually ends up impacting the Arctic too. So very large scale teleconnections sometimes that you see. But I would suppose, Clara, that this is true, that the reason why you have this asymmetry in the dynamics of the polar cell between the hemispheres is probably the presence of this high elevation continent.
Thanks. Dave, you're up next.
Sure. So Hansi, the tracer analysis is really cool. I think that's a neat tool to have in your toolbox and everything. And I think you said that the moisture that gets up onto the high plateau actually comes from further north, whereas the stuff in the lower elevations comes from closer to the continent. So I'm kind of curious. That seems kind of counterintuitive to me, but I mean, do you know about the mechanism for that? Like, have you looked at the pathways that it's getting there, or is it just that it's such a tiny amount getting up there,
Yeah, that's a good question. So if you look at our 2019 paper that Adriana Bailey led, sorry, just going to go backwards. Essentially, if you look, so this is the moisture sources over the Antarctic continent by pressure level. What you really see is, I mean, these literally look like some beautiful radiative transfer weighting functions. Like they're so pretty. You just see that moisture that is coming from closer really dominates closer to the surface, and moisture that is coming from further away comes in at these sort of higher elevations. And if you look at each latitude band, this is just showing the 30 south to 40 south latitude band, you see that they really do follow these moist isentropic surfaces. Okay. So this is work that like Olivier Polius and colleagues did maybe like 10 years ago. They did a lot of theoretical work thinking about the atmospheric circulation on moist isentropic surfaces. And, they really said that it looks like, if we think in terms of moist entropy, that we can consider the circulation to essentially conserve moist entropy. Not completely, it's a little lazy. There are diabatic processes that happen, but certainly the extrapolar circulation generally seems to follow that. And so, yeah, I mean, this is kind of what you see, that from each of these latitude bands, you really do follow these moist isentropic surfaces quite well.
Cool.
Excellent. Well, we're approaching the top of the hour. So Hansi, thanks once again for sharing your work, and thanks everyone else for participating. And we look forward to seeing you all next week. Take care.
Thanks, Dan. Thank you all.